Good morning, everyone, and welcome to the lecture on the most awaited topic, rotation. As soon as I say the word rotation, this chapter may also be known as by a different name, and that different name is rigid bodies or dynamics of rigid bodies or rigid body dynamics, rigid bodies or rigid body dynamics. Now, what is going to happen in this chapter is up till now, not up till now, we were taking bodies as particles. We were basically dealing with them, thinking them as particles and dealing with them. In this chapter, we will deal with them as bodies because they would have some shape, they would have some size, and therefore we will be dealing with them as bodies. So now, if there is a rod and there is a disc, their motions would be defined by their shape and just not treating them as a particle, whether it's a car, whatever shape, rod, whatever shape, man, whatever shape, he has the same motion. Now the motion depends on the shape because now we come into that scenario where we talk about the shape of that bodies. Now, in this chapter, we will be dealing with rigid bodies. So, first of all, we need to understand what do you mean by a rigid body. What do you understand by a rigid body? Here, the bodies are not going to change in size or shape. That will come in the chapter on elasticity when size and shape and dimensions are going to change. What do you understand by a rigid body? Is the first question. What do we understand by a rigid body? Anyone? What is a rigid body? Huh?
A body which has no deformation.
A body which has no deformation. What do you mean by deformation? It does not change its shape or size. Well, that is an okay way of defining it, but the correct way obviously does not change its size and shape when forces act on it. That is one way of defining it, but is not the very correct way of defining it. The most correct way of defining a rigid body is like this. It is defined as a system of particles. It may not be a body. You must understand. It may not be a body. It may be a system of particles. If it is a body, okay, it may be a body, but it may also be a system of particles in which the distance between any two pair of particles remains constant. The distance between any two pair, if I talk about any 2 points on that particle, and if the distance between them remains constant, then we call such bodies as rigid bodies. No matter how the body moves, the distance between any two particles, any 2 points must remain same. Do we understand this? That is actually what we mean by a rigid body. Should not change its size and shape, but the better way is the distance, whatever happens with that body, the distance between any 2 points on that body should not change. So if I have a body like this, it could be of any shape, it could be a system of particles, and I take 2 points A and B. The distance between these 2 points A and B, whatever the distance B, should remain same. Then we call that body as a rigid body. Do we understand this? But as said, it may not be a body. It may be a system of particles as well that can act as a rigid body. Just to give you an example, this system which you see in diagram number A or B, this consists of two different bodies. In fact, it consists of three bodies. It consists of body of mass, a body A, a body B, and a spring. Now, if both the blocks are moving with the same velocity, the distance between any 2 points does not change. This system of particles can also be treated as a rigid body. Do we understand this? This entire system can also be treated as a rigid body. Do we understand this, or this has gone above our heads?
Yes, sir.
So, this is what you mean by a rigid body. Now, since the distance between any 2 points, does not change, there is no change in the distance between any two points that you take, the size and the shape of the system will remain constant or remain same. So that is the next way of understanding what is a rigid body. The first way is distance between any two particles, any 2 points should not change. The second one is, since the distance does not change, then the size and the shape of that body will remain same. Do we understand this?
Yes, sir.
Have we noted it down, bacha? Huh?
1 minute.
Okay. Let me know once you're done.
Yes, sir.
Everyone done? Now, a very important thing that you must understand. We had seen relative velocity in some days back, 10 or 15 days back, but we just saw it, relative angular velocity and relative this velocity. Now remember, between any two pair of particles, there is no change in distance. The distance must not change. That means if I take any two pair of particles, there will be no velocity of separation or velocity of approach if the body is a rigid body. Do we understand this? There should not be any velocity of separation or velocity of approach, because if there is any velocity of approach or velocity of separation, the distance will change. Yes or no? Yes or no?
Yes, sir.
That means the relative motion of any point A with respect to any point B, to take any point on the rigid body, and you take any other point on the rigid body, the relative motion is going to be a circular motion. Do we understand this, or this has gone above our head saying bye bye? I'm going. Bye bye. It cannot be bye bye because that is the main concept of this body, rigid body. There is no velocity of separation and there is no velocity of approach. So whatever happens, there should not be there should not be any change in the distance. There should not be any velocity of separation or velocity of approach. So that gives us a very important concept. If these are 2 points, you can see these 2 points A and B are 2 points on a rigid body. Now, since we know that this entire thing is a rigid body, and if someone gives us the velocities of A and velocities of B in this way, we can easily find out simple equations based on their velocities. Yes or no? What equation can we write looking at this diagram? If we know that this is a rigid body, it can move in any random fashion, doesn't matter. We can write some equation based on this. What equation can I write based on this? Tell me. Knowing that there should not be any velocity of separation or velocity of approach. We have just discussed this. Can you tell me? What equation can I write? Huh? No one? Huh? No one knows this. There is no velocity of separation or the velocity of approach. So if I resolve their velocities along the line joining the two particles, this is the line joining the two particles. If I draw their velocities, they must be in the same direction, in the same sense, and one equation must be fulfilled. VA cos of theta 1 should be equal to VB cos of theta 2 because there is no relative velocity of separation, or velocity of approach. Do we understand this, or this has gone above our head saying bye bye? I'm going, don't worry about me. Now, if I tell you that the distance between point A and point B is, let us say, r, perpendicular distance between point A and point B, you can also find out the angular velocity of A with respect to B or B with respect to A. Can you tell me what will be the value of the angular velocity of A with respect to B or B with respect to A? Huh?
Sir, VA sin
VA
theta 1 minus VB sin theta 2
plus VB sin theta 2
by R.
by R. This will be the angular velocity what B sees A moving. A will also see with the same velocity B is moving around it in a circular path. With respect to any point on the rigid body, any other point will be moving with the same angular velocity. Am I clear, or this has gone above our head saying bye bye?
Yes, sir, you are clear.
This is a very important concept. About the rigid bodies, there is no relative velocity, there is no velocity of separation, there is no velocity of approach. The relative angular velocities should be same. When understanding the important concept, have you noted it down, bacha? See, you can understand this by this example. If you take any 3 points, A, B, and C, and you make a triangle, remember this is a rigid body. So, if AC turns by some angle, BC should also turn by the same angle with respect to any point, and AB should also turn by the same angle. Do we understand this? So, their relative orientation must remain same. Do we get this? Yes or no?
Yes, sir.
Because all the points with respect to any other point must move with the same angular velocity, and you can find out the angular velocity. You find out the velocities of these particles perpendicular to the line, and you divide it by the radius or distance r. Do we understand this? Yes or no? So
Yes,
this is
sir.
just for you to understand what is a rigid body. I'll give you 2 minutes to note it down. You may not have to note down the entire concept. Just understand what do you mean by a rigid body.
Sir, it's done, sir.
Everyone got it? Yes or no? No, yes. Huh? Everyone noted it down? Now, since we have understood what is a rigid body, now we can understand the type of motion of a rigid body. What type of motion a rigid body can have? What type of motion a rigid body can have? Huh? What do you think? What type of motion a rigid body can have? How many types of motion a rigid body can have? Hmm.
Translational, rotational, and rotational translation.
The first type of motion is pure translation. The second type of motion is pure rotation. And the third type of motion, sometimes you can call it combined or plane motion, which is a combination of translation and rotation. Actually, there is no need to classify them as three. You can only call it as type 3. The motion of a rigid body is a combination of translation and rotation. Sometimes rotation is 0, it is pure translation. Sometimes translation is 0, it is pure rotation. Sometimes it can be a combination of all the three together. The first type is pure translational. What do you mean by a pure translational motion? Huh?
Motion in a straight line.
Motion in a straight line is pure translation. If this body moves like this, is this translation or rotational? Huh? A car moving on a hill, up and down. Wee, 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 wee. Huh? Rotation. Car is rotating. Say, only motion in a straight line is pure translation. There is no other motion which is translational. Is that what you want to say? Huh? Now I'm confused. Say, straight line is obviously translation, but only straight line is translation.
No, sir.
No, sir, then why did you say straight line? See, you take any motion like this. This is a rigid body moving from point A to point B. You can take these two examples of pure translational motion. Here, in first case, your body moving like this. It could also move like this. Now, How can you tell me what is pure translation? You take any particle on the body and you take every particle on the body. If the velocity, displacement and acceleration are always same, all particles of the body have the same velocity, they have the same acceleration at all times, the velocities and accelerations and displacement at all times is same, then the motion is known as pure translation. A body is said to be in pure translational motion if the displacement is same, all particles have the same displacement, same velocity and same acceleration at all instants. Whatever be the value, they must have the same value. So, what do we understand by pure translation if I write it point wise? Number one, they must have same,
Displacement.
all particles must have same displacement, same velocity and same acceleration at all times. This is one way of writing it. The second way of understanding this is you can write it like this. There is only change in its position, not its orientation. Change in its position. The body only changes its position and not orientation. The orientation of the body should not change. You understand the meaning of orientation? If the body is like this, if it always remain like this, if the body is like this, it always remains like this, then this motion is translation. Do we understand this?
Yes, sir.
This motion is translation. But if it happens, it happens, it happens, that means the orientation of the body is changing or the plane of the body is changing. From this plane, it comes to this plane. Orientation or the plane of the body should not change. Only its position should change. Do we understand this, or this has gone above our heads saying bye bye? I am going, don't worry about me. Huh?
We understood that, sir.
That type of motion is known as pure translation. A point mass. You understand the meaning of point mass? A point mass only has translational motion. Do we understand this?
Yes, sir.
A point mass only have translational motion because it is a point. It does not have any orientation. Even if it changes the orientation, you will never know because it is a point mass. So point mass only has translational motion. Up till now, what we were doing was translational motion. Even that circular motion was translation. If a body like this moves in a circle and its plane does not change, it is pure circular motion. Do we understand this? Unless and its plane changes, it is not rotation. So whenever we were saying circular motion, we were treating bodies at point masses, and therefore the motion was called circular. Do we understand this, or this has gone above our head saying bye bye? I'm going. Don't worry about me.
We understood, sir.
Pure translation. Now, in pure translation, the velocities of all the particles, if I call the particles as v1, v2, v3, v4 up till vn, all their velocities are same as v, all their accelerations are same as a. So instead of treating them as a collection of different points, we could treat them as one point. Do we understand this? There is no point of treating them as other points, because all of them have the same motion. So we treated them as one point, and we introduced the concept of center of mass. Do we understand that concept of center of mass?
Yes, sir.
We treated that, oh, this is not a body, no problem. We can treat them as a point, and we only have to understand the translational motion of that point. We'll just study the motion of which point. You could have it could have been any point, but we took one point which was known as the what?
Center of mass.
Center of mass. So here comes a very important concept. The motion of the center of the mass of the body describes which motion of the body?
Translation motion of the body.
Whenever you are studying the motion of the center of mass of the body, you are studying the translational motion of the body. Do we understand this, or this has gone above our head saying bye bye? You can write this as the next point. The motion of the center of mass of the body. And therefore the center of mass will come again in this chapter. The motion of COM tells us the translational motion of the body. Do we understand this? So you can write this as ACOM, and you can write this as VCOM. I hope you are understanding this.
Yes, sir.
What, sir? Which acceleration I have said, sir? Huh? You understand this, no? Every point that I am saying is like gold dust, my dear friend. Gold dust, stardust, gold dust. Should not be missed, whatever happens. Now, if you talk about the external force, there may be external force, more than one external force acting on the body, F1, F2, F3, and so on. I told you internal forces cancel, yes or no?
Yes, sir.
So the net external force can be written as total mass into ACOM. This is only for the translational motion. Do we understand it?
Yes, sir.
Translational motion. If we write P1, P2, P3, P4, M1, V1, M2, V2 as the momentum of the individual particles of the body, we can add them all. And we will get the momentum of the center of mass, the linear momentum of the center of mass. Linear momentum, do we understand this? Translational motion, linear momentum of the center of mass, which comes because of the translational motion of this rigid body. I hope you understand this.
Yes, sir.
Then the next thing that we studied was the total kinetic energy of the body. And we can now write it as half into capital mass M into V square, where V is the velocity of the center of mass. You must understand that all the bodies are moving with the same velocity. Yes or no?
Yes, sir.
So for translational motion, remember whatever we are writing is purely for translational motion. Purely. Now we have studied this motion in all these chapters, so obviously we are not going to study pure translational motion. Huh? Yes or no?
Sir.
We already studied this motion for the past 6 chapters. We have been studying this. We have been treating bodies as particles. We have been treating bodies as point masses. So there is no point of studying this motion. So which motion we should study now? Huh? Pure translation is already done. We have done it for previous 7 chapters. What is the next type of motion that we must study? Huh?
Pure rotational.
Pure rotational. Pure rotational motion. Right? Why am I writing motion? Motion. Pure rotational motion. And I told you, circular motion is not rotational because it is translational. Then what is rotational? What is pure rotational? Huh? Tell me, what is pure rotational? Circular is not rotational. For circular transition. No one knows this? Huh? You have not seen pure rotation. The fan on top of you is in pure rotation. It is not moving right now. That is pure rotation. You have not seen a fan turning ever in your life? Seen, no? So that is pure rotation. Tell me what is pure rotation.
I can't get the correct wording, sir.
कोई बात नहीं. Try your wording. I will somehow manipulate it. Give me your version of rotation. What is rotation? I was 5-10 years back. I went for interview. Wanted a job, and I mean there was a job, and they called me, sir, please come. We need you. I said, okay, I'll come. No worry. I went there. And there were 2 small kids who were taking my interview. I mean, I probably would have taught people of their age. So these kids are asking me, sir, on what should I take your what interview? I said, ask anything, whatever you want. I knew what will they ask. So, sir, we'll ask about rotation. I said, okay, fine. Ask rotation. I'll rotate you, don't worry. So they asked it that, sir, what is the difference between sir, what is rotational motion? So I gave them my definition, and they looked at each other's faces. Sir, relation between rotation and circular motion. I said, beta, there is none. They rejected me, of course. Oh, most of these stupid people, they think that rotational is circular motion. Rotation is not circular. Rotation is transition. I told them that, and they were again looking at each other's faces. They were thinking that I am mad. Actually, they had no knowledge about it. This what you see, my dear friend, is pure rotation. Your body. This phone, whenever I pick up, it wakes up. This is a body. It could be of any size, any shape. Now, you can see these points. It is made up of a large number of particles. Now, if all of these particles are moving on a circle, the motion of all of these particles are on a circle. Now, since this body is three-dimensional, those circles ka center cannot lie at one point. So, their centers of circles may not lie at one point, but they may lie at one line.
Line.
So, if a body is moving in such a way that all particles of the body are moving in a circular path, and the center of all those circles lie on one fixed line or one line, that motion is known as pure rotational motion. That line on which all their centers lie is known as the axis of rotation. So here you can see M1, M2, M3, they are different particles lying on the same body. They're all moving on a circular path. You can see this one. This is the circular motion of particle 1. This is the circular motion of particle 2, and this is the circular motion of particle 3. If any shape body, any type of body, rigid body of any shape is moving in such a way that all the particles of the body are moving in circular path, the center of those circles should lie on one line, not two different lines. If there are two different lines, it's not circular, it's not rotational. Then the motion is known as pure rotation, and as you can see, all of them will then rotate with the same angular velocity. They will turn together by the same angle. Do we understand this? And this omega is then known as their angular velocity of rotation, which is same as the angular velocity of circular motion of all these particles. Do we understand this? Yes or no?
Yes.
This motion is known as
Pure rotational motion.
This motion is known as pure rotation. If you want to write it, you can write it in language in this form. The angular velocity omega can be found out by dividing v1 by r1, or by dividing v2 by r2, or by dividing v3 by r3. Do you understand this? So this angular velocity omega will become v1 by r1, which will be equal to v2 by r2, and so on. Every point, so you can note them out point wise. Every point, every particle moves, or every particle follows circular motion. Center of all circles lie on same line. That line is known as axis of rotation, and their common angular velocity is known as the angular velocity of rotation. Do we understand this? Or this has gone above our head saying bye bye.
We understood, sir.
So as you can see, note it down. You want to note it down?
Sir, it's done, sir.
Everyone done, sir? Huh? Okay. Now here is the time that I can introduce the concept which is going to come next. And this is the best way I have found out to introduce this. And I will try the same trick with you. Now, the body is in pure rotation. Now, when the body is in pure rotation, you can find out the total kinetic energy of the body. And it will be given by this half m1 v1 square plus half m2 v2 square and so on. Yes or no?
Yes, sir.
Now, v1 can be written as omega into r1. V2 can be written as omega into r2 and so on. So I can keep this everything constant and multiply it by the angular velocity omega square. Yes or no?
Yes, sir.
Now this entire blue thing can be written as, wrong color. This entire blue thing can be written as I m1 r1 square. This new term, I is summation of mi ri square. Do we understand this?
Yes, sir.
This I came to be known as or is known as
Moment of inertia.
moment of inertia. And this is the concept that is going to come now. This is the concept that is going to come. I'll give you 2 minutes to note it down. Have you noted it down?
Yes, sir.
Huh?
Yes, sir.
Will you move on?
Yes, sir.
Okay. Now, whenever we talk about this pure rotational motion or rotation about an axis, we can have 3 different cases of this rotation of a body on an axis. The first case is rotation about an axis which is fixed. Now, in this case, since the axis is fixed, since the axis is not going anywhere, this becomes your case of which motion? This becomes your which motion? The axis is fixed. Axis is not going anywhere. This becomes which motion?
Pure rotation.
This becomes pure rotation. Pure 100% rotation. This becomes pure rotation. Rotation about a fixed axis is pure rotation. Then what is the second one? Rotation about an axis which is in translation. Rotation about an axis which is in translation. That means this will become combined.
Combined.
Combined what? Translational plus rotation. The third and the most difficult type is rotation about an axis which is itself in rotation. Now, this is not in your JEE course, so we'll just skip this part. Rotation about an axis which is in rotation. So, rotation about a fixed axis, and we are going to do them one by one. Rotation about a fixed axis, rotation about an axis in translation, rotation about an axis in rotation, We are not going to discuss it at all. So now we come to rotation about a fixed axis, and that is what we had seen. Rotation about a fixed axis. This is in fact your pure rotational motion. Now, can you give me an example of pure rotational motion, my dear friend? Huh?
Giant wheel, sir.
What, beta?
Giant wheel.
Giant wheel. Okay. A ceiling fan is an example of pure rotation. A giant wheel is an example of pure rotation. There is a door that you must have crossed when you have come in the class. That is also an example of pure rotation, right? Now you
Yes,
look
sir.
at all these examples. You look at any point on the ceiling fan, it is moving in a circular path. Yes or no?
Yes, sir.
About an axis which passes through this line. That becomes your axis of rotation. You don't have to draw this typical diagram. I can't draw it. That's why I'm using it. Look at this door also. All the points are moving on a circle. The center of all those circles lie on a fixed line. Yes or no? That is your axis of rotation. Do we understand this?
Yes,
Yes
sir.
or no? No or yes? Huh? Understand this? No?
Yes, sir.
You can also see the motion of this disk. It is in pure rotation. Yes or no?
Yes, sir.
What are the important points that you must remember? We have already discussed them. We will just go through them once again. You understand this now?
Yes, sir.
So the first point that you must remember about fixed axis rotation is all the particles are moving in circles. But remember, those particles must not be on the axis of rotation, because if this particle is on the axis of rotation, it is not moving at all. Do we understand this? On the axis of rotation, no one moves. They move on circular path. Their centers are on the axis of rotation. All these circular paths are parallel planes which are perpendicular to the axis of rotation. Do we understand this, or this has gone above our head saying bye bye, bye bye, sir, I'm going, don't worry about me?
We understood, sir.
Okay. Why I'm putting so much effort in making you understand this? Because it is important that you understand what is pure rotation. And that this transition wala concept should not come into your head. I will tell you all those points, then you can write them. Okay, let me just carry on. So just listen to me, then you can write. All the particles have same angular displacement, same angular velocity, and same angular acceleration. We understand this?
Yes, sir.
They have the same angular quantities, but if you talk about their linear quantities, their transitional velocities, their tangential velocities, they are all going to be different if they don't lie on the same radius. Do you understand this?
Yes, sir.
Okay, so they are moving with different radius, with different speed and different magnitude of linear acceleration. We understand this?
Yes, sir.
Okay. Now this is the same thing said in a different way. You may not remember this. All the particles on a line which is parallel to the rotation move in the circular paths of same radius, therefore have same velocity and acceleration. You just understand the basic concept. Do we understand this?
Yes, sir.
Okay. So we have understood this, yes or no? Just take this. It's enough for you to understand the concept of rotation motion. And you just write everything in short, okay? Don't have to write the entire thing. Just for your understanding. Have you noted it down?
1 minute, sir. Done, sir.
Anyone done? Yes or no?
Yes, sir.
Now see, now we are talking about digit bodies, so we must take in consideration their shape. It is like this. Remember, its orientation has changed. Its orientation has changed by angle theta. So this theta becomes your angular displacement. Do we understand this?
Yes, sir.
So this is angular velocity. We have seen this angular velocity in circular motion. It has the same meaning. Now the only thing we have to understand that there is an axis of rotation. Now I told you that all these angular quantities are axial vectors. Did I tell you that? Yes or no? So bodies rotate on an axis. These are axial vectors. So if it's rotating like this, the displacement would be like this. Your angular velocity would be like this. Do we understand this? Yes or no?
Yes, sir.
So these are axial vectors. I hope you are understanding the meaning. So same terms will come here. The terms that had come in your circular motion, in those circular motion, they were the same, right? Now, instead of a point moving, this is an entire body moving. Do we understand this?
Yes, sir.
Axial vectors. Then alpha is also an axial vector. If alpha and omega, they are along the same axis, the value of omega will increase. Do we understand this?
Yes, sir.
If they are in the opposite direction, omega will decrease. Yes or no?
Yes, sir.
That means we are doing the same thing that we were doing for translation as rotation, or we were doing it in the circular motion. Do we understand this?
Yes, sir.
Same equations are still valid. We have done it before. Just now we had done it. Yes or no?
Yes, sir.
Just completed circular motion and came here. Just to give you a quick recap, these are the equations. I don't think anyone has any problem with this. Yes or no?
Sir.
Pure rotation can be taken as circular motion because all the particles are moving with the same angular velocity. So we can, problem wise, we can treat it as a problem of pure circular motion. It is not circular motion. All the particles are moving in circular, but the body is rotating. Do we understand this?
Yes, sir.
Okay, just to give you an idea, let me put this question. Now, instead of a body moving in circular path, you will have things moving on a rotational motion. I hope that does not make any difference. Solve this question. I give a wheel is rotating with an angular velocity of 2 radians per second. It is subjected to a uniform angular acceleration of 2 radians per second square. How much angular velocity does the wheel occur after 10 seconds? How many complete revolution does it make in the complete time interval? And the answer is, huh?
Sir, angular velocity is 22 radians per second.
Okay.
Revolutions we are doing 1 minute.
Okay.
Sir, Complete rotations is 3, sir.
How did you get 3 rotation?
The free
Huh? 3 rotations. Okay. Tell me, how did you get it? Where is the pen? Who is this KVC who wants to enter? Yes. How are you supposed to solve this? No one got the answer. Shame. Omega 2 is equal to omega 1 plus alpha t. You put the values, you get the answer. What is the value of omega 2 coming as? 22 rad per sec. How do you find out the complete revolutions? Yes. What is gone? How will you get the complete revolution? So for that, you have to find out the angular displacement. Omega 1 t plus half alpha t square. You can put the values of omega 1 and alpha and you will get the angular displacement. How much is the angular displacement coming as? Huh? How much is the angular displacement coming as? Omega 1 is 2, time is 10, 2 into 10 is 20, plus half into 2 is 1, 10 square is 100. How much is it coming? Hundred and 20. It's coming 120? Yes or no? 120 radians. So how many number of revolutions? 120 divided by 2 pi. These many number of revolutions. What problem did you face? Tell me. What was the problem in getting this answer? Huh? What was the problem? Tell me. You have forgotten the basic equations. Your mic is not working. You have forgotten the basic equations. 2 days before I told you this equation. And everyone has forgotten and now sitting and chilling out. Shame on you. I thought that this is already done. Chalo, then solve these problems. What to do? You've forgotten the basic premise, how to solve questions. You have to do more problems. Okay, we'll do this one then. The wheel of a motor accelerated uniformly from rest rotates through 2.5 radian during the first second. Find the angle rotated during the next second. You have 2 minutes to do this. 7.5 radian. That is correct. Chalo, we have an answer at least. After so much time, we have an answer. So, there are number of ways in which you can have done this. You could straight away apply the formula, or you could apply the formula for the nth second. Do we understand this? The initial angular velocity is 0, omega 1 is 0. So you can do it in two ways. The first way is you apply the formula for displacement in the nth second. Displacement in the first second will be omega 1 plus alpha by 2 into 2 into 1 minus 1. From here you can find out omega is given as 0. You can find out the value of alpha. Do we understand this? Yes or no? Then you can put the formula for displacement in the what is this? Then you can put the formula for displacement in the second initial velocity omega plus alpha by 2 into 2 into 2 minus 1. This omega 1 is 0. You have already calculated alpha from equation number 1, or you don't want to calculate alpha from equation number 1. Divide these two equations. Alpha will get cancelled and you will get displacement in the second. Do we understand this? Yes or no? Okay, one more last. Do it fast, so that I have confidence that we are done, because you may have a simple question like this in the examination hall. I don't want you to miss on that question. So this one, the motor of an engine is rotating about an axis with an angular velocity of 100 revolution per minute. It comes to rest in 15 seconds after being switched off. Assuming constant angular deceleration, calculate the number of revolutions made by it before coming to rest. You have 2 minutes to do this. Yes, my bacha. No answers. Huh? Not expected. Simple question. You should have given the answer. 12 revolution. The answer is 12.5 revolutions. The angular displacement is 25 pi radians. Did you get 25 pi? Yes or no? No one got the answer. Everyone is looking at each other's faces. The answer is not there in the faces. Yes, sir. But you have taken too much time, sir, for solving this simple question, sir. That is when we are doing the topic, sir. What will happen after 5 months, sir, when you have read the topic before 5 months, sir? What will happen then, sir? You are taking 4 minutes to solve this question here in the class when we are doing the topic. What will happen after 5 months when you will not even remember which topic is this? You should have done it faster. This is omega 1 given to you. It comes to rest. So omega 2 is 0. Time is given to you. Omega 1 given. Time given. Omega 2 given. Constant angular deceleration given. You had to find out the angular displacement. You could have used this beautiful equation. But no, you will not remember it. The problem is all of you have become Gajnis, lady Gajnis and male Gajnis. Put this formula, get your answer, stay happy. 100 by 2 is 50. 50. 100 by 2 revolutions per minute. So you divide it into seconds. So this is 100 divided by 60 into 2 into 15. 15 1 the 15, 15 4 the 60, 2 1 the 2, 250 the 100. 50 divided by 4, 12.5. Even if as a kid I can do it in 6-7 seconds with writing and explaining, you took bloody 4 minutes to do this. What is the benefit of taking classes from me if you have to take so much of time to solve this? That too after studying circular motion for so long. Rotation motion again, I was not planning to do all these questions because we have just done it 3 days back. Anyways, I hope better sense will prevail. I am really losing confidence. If I have to do these questions again after so much of time, there is something wrong somewhere. Anyways, I can't do any more because I'm done with all the questions. So I'll have to move forward. And I hope that better sense will prevail. I've sent you a rotation ka sheet. Send you a rotation ka sheet. There are a few questions on this. I hope you will be solving them. I'm really disappointed, but anyways, I have to leave my disappointment at what it was and move ahead in life. Life has to move on. I just cannot keep on doing the same questions over and over again. So the next heading that we have is moment of inertia. Remember, you had to use only 3 equations. V is equal to u plus at, s is equal to ut plus half at square, v square equal to u square plus 2s. I gave you that average valid equation. If you can't use them, I have no words to say. I'm really disappointed. Anyways, leaving disappointments apart, I come to this moment of inertia denoted by the legendary letter capital I, not small I. Capital I is not small I. Now you can't speak, so I can't even ask you what is moment of inertia. But what is moment of inertia? What is inertia? Now you cannot speak. That is the problem. What is inertia? Inertia was, if I talk about inertia, it was in chapter 4 or 3 or whatever. Inertia was a property. Oh, not, I should not write was. Inertia is the wrong color. See, I am so disappointed that I have lost the sense of color. Inertia is the property by virtue of which a body resists any change in its translational motion. So, If your body and you want to change its translation motion, it will resist any change in its translation motion. That property is known as inertia, my dear friends. Just a recap. Then what is moment of inertia? Moment of inertia, MIs. Not mission impossible, but moment of inertia. But for us, even simple things get mission impossible. And everyone has to become Tom Cruise and hang from the helicopter and save the day for save the world. We're not Tom Cruises, and this is not mission impossible. This is mission IIT. It's as simple as it gets. But you'll have to pull up your socks a bit. And remember, you'll have to think about the quickest way of getting to the mission MI, not the longest way. Because if you take the longest way, someone else will become Tom Cruise and take your heroine or girl or your prize or gift or world, whatever. Look for the quickest one. What is MI? It's not motion impossible, it is moment of inertia. What is moment of inertia then? Inertia resists any change in its translational motion. That is a hint. So what is moment of inertia? Huh? Mic does not work. That's a good excuse. We don't know the mic doesn't work. Let it go. Moment of inertia is a property by virtue of which any body resists any change in its rotational motion. Same thing. You have to write the entire definition. The only thing that will change is this rotational motion will come in place of this translational motion. So moment of inertia MI, mission impossible, is the property by virtue of which a body resists any change in its rotational motion. Do we understand this, or this is going about saying bye bye? I'm going, don't worry about me. Right. 2 minutes to write it. Have you written this? This moment of inertia, MI, does the same job. MI does the same job. Moment of inertia, or I, does the same job as what? Mass in linear motion. Mass in linear motion, my dear friends. Moment of inertia in rotational motion. We come back to this. In linear motion, we have mass m. In rotational motion, we have I, moment of inertia. Same job, same thing. Mass is a measure of the inertia of the body, the property by virtue of which it resists any change in its translational motion. Moment of inertia does the same thing for rotational. Do we understand this? Yes or no? No, yes. Huh? Now, what is the formula for moment of inertia for a particle, for a point mass or a particle? For a particle or a point mass, and we had seen it, the moment of inertia is m into r square. What is m? What is r? Huh? What is m? What is r? M is the mass of that particle, and r is the distance of the particle. So if I have a mass m1 here at a distance of r1, from the rotational axis. Its moment of inertia about the rotational axis would be m into r1 square. The m1 into r1 square. The moment of inertia for this body will be m2 into r2 square about this axis of rotation. The moment of inertia of the ith body will be mi into ri square. So now if you have a system of n particles, for a system of n particles, for a system of n particles, only particles, the total moment of inertia will be the summation of mi ri square. Do we understand this? Yes or no? No, yes. For a continuous body, this is not a system of particles, this is a continuous body. For a continuous body, moment of inertia I will be integral of the small mass dm into r square. Do we understand this? Yes or no? No, yes. Mr. Gone about it saying bye bye. I'm going, don't worry about me. Huh? Now, on what all factors the moment of inertia of a body or a system of particle depends on? The moment of inertia depends on the density. The density is uniform. You will have, if the density is different at different points, the moment of inertia will be different. Size and shape. If more mass is near and less mass is away, the size and shape, if it is irregular size, irregular shape, moment of inertia will change. It also depends on axis of rotation. In short, you can say in point number 4, it depends on the distribution of mass around the axis of rotation. How is the mass distributed? It depends on the axis of rotation, it depends on the size, shape, it depends on density. Basically speaking, depends on the distribution of mass in very short and sweet terms. We now talk about its dimensions and the SI unit. The SI unit becomes kg into meter square, moment of inertia. The dimensions become ml square. Do we understand this? Yes or no? No, yes. What type of quantity is moment of inertia? It is not a scalar. It is not a vector. What type of quantity is moment of inertia? It's not a scalar. It's not a vector. It's not a vector because it does not depend on direction. Clockwise or anti-clockwise rotation, it does not depend on direction. It's not a scalar. It's not a vector. It's not a scalar because it depends on the axis of rotation. Therefore, it's not a scalar, not a vector. We call it tensor. Not a scalar, not a vector. We call it tensor. Do we understand this? Yes or no? Just gone above it saying bye bye. Bye bye. Don't worry about me. I'm gone. Out. Okay. Now you'll have to remember a few moment of inertia, and the more the moment of inertia you can remember, the better it is going to be for your health. But before going on to that, let us finish some important things, and this is the important thing. Let us solve some question based on simple things, because it's all about solving questions. The questions are going to come on questions and not on anything else. Four particles are here like this. Four particles is of mass m are kept at the four corners of a square of edge A. Find the moment of the inertia of the system about a line. Remember, it depends on the axis of rotation, so you must understand clearly what is the axis of rotation. About an axis of rotation, about a line which is perpendicular to the plane of the square and passing through the center of the square. The side of the square is given as A. So you have to find its moment of inertia about point O perpendicular to the plane of the paper. Do we understand this? Yes or no? Huh? I'll give you 2 minutes to do this. Huh? So what is the answer? 2ma square, that is correct. The moment of inertia of all the particles will be same, all masses are same, and you have to find out this distance. You were lucky that this distance was given as m by root 2. You understand? A by root 2, we understand this? So what is the moment of inertia of all the four particles? It will be 4 times m into a by root 2 ka square, and your answer will become 2ma square. Everyone got this? Yes or no? Now I'm asking you the second question, the green question. What is the moment of inertia about the axis AB? AB is an axis which passes through one of the sides. AB is one of the sides. What is the moment of inertia about the axis AB if AB is your axis? So, how do you get this moment of inertia about this axis? Well done. About the axis AB, the moment of inertia of this block will be 0 because it lies on the axis. The moment of inertia of this body will also be 0. You just have to find the moment of inertia of this one, which will be equal to m into a square. You have to find the moment of inertia of this one, which will be equal to m into a square. So finally, your answer is same as the previous one. No. M into a square plus a square. So the final answer is 2ma square. Do we understand this? Yes or no? Now it seems like moment of inertia in both the cases are coming same. Okay, let us do the third question. What is the moment of inertia about the axis AC? Everyone is understanding what we are doing here? Yes or no? Comes the third question. What is the moment of inertia about the axis AC? This is A, this is B, this is C, and this is T. So in one question, we can do all types of question. The basic premise of doing this question is to understand that the moment of inertia depends on the axis and the distribution of mass around the axis. I'll give you 1 minute, then I'll solve it. Don't have to come to the board to write the answer. I'll just solve it after a minute. What is the moment of inertia about the axis AC? Yes, it will be equal to ma square. How do we get this? About the axis AC, this mass lies on the axis, zero moment of inertia. This mass lies on the axis, zero moment of inertia. You just have to calculate the moment of inertia of this one and this one. Masses are same. So you just multiply. You find the moment of inertia of one and multiply it by 2. Moment of inertia of any one will be distance is a by root 2. A by root 2 ka square. 2 times m into a by root 2 ka square, it is ma square. As you can see, this moment of inertia is coming different because the distribution has changed. Last, in this category, find the moment of inertia about an axis passing through A and perpendicular to the plane of the board, like this. Passing through A and perpendicular to the plane of the board. So I call it passing through A and perpendicular to the board. Four ma square. Well, how do you get this 4 ma square? Passing through A, moment of inertia of this block is gone. The moment of inertia of this block is ma square. The moment of inertia of this block is ma square. So ma square plus ma square becomes 2 ma square. Do we understand this, or this is going above it saying bye-bye? Plus, you have to find the moment of inertia of this block, the distance of this block, perpendicular distance of this block from the axis is root 2a. So it is m into root 2a square. So your final answer becomes 4 times ma square. The only purpose of doing this is to make you understand that depending on the axis, the moment of inertia changes. We will not do more problems on this. You can do it from the exercise that I have sent you already. We will move on to the moment of inertia of some geometrical bodies, and I hope you know the moment of inertia of some of those bodies. Yes or no? So we'll move on to those bodies, and I will send you a list probably, and I will ask the office people to send you that list, give you the printout today now only, so you can have the entire list of all the bodies for your reference. Okay. So then I will wind up this class here. I hope you have understood this, and please, 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 please practice more. Okay. Take care. God bless you all. Bye bye.